Here, let me see. So this is not a terribly well-prepared talk. It is really, it's a quick status of what happened since last year in Nuremberg. When we met in Nuremberg for XDS in 2012, we were just about to ship 1.0 of Wayland and Western, and that did happen a few weeks later. And with the 1.0 release, we now have a stable, or we've had a stable client-side API since the 1.0 release. So any toolkits, anything you do on the client side is now written against a stable API, and protocol is stable. So you could potentially write client-side binding in a different language if you want. And a little later, we so there are two sides to the core Wayland API. There's the client side, which toolkits and clients talk to, and there's the server side, which you use if you write a server like Western or GNOME Shell. So a Wayland compositor will use a server library to set itself up as a server and accept incoming connections and receive requests. And this part was something we weren't ready to stabilize with 1.0. So for 1.0 and the later 1.1 release, we didn't have a stable API, but about a few months ago, we released 1.2, and from 1.2 on, we have a stable server-side API now. And this becomes more important now as GNOME Shell is preparing to ship with Wayland support. And there are a few other compositors out there that use the server-side API. So having a stable API there makes a lot of sense, so we don't break things for these other compositors with every release. And the trick to getting a stable API was to pull the code out that we couldn't stabilize and pull it into Western. And we were trying to split some input logic between the server-side library and Western, and turns out that was a bad idea, and it was really hard to get an API that was maintainable. So we just moved into Western, and what's left in the server-side library now is more or less exclusively IPC and the core protocol definition. So there's not much there, but it's enough that you can become a Wayland compositor and then hook that into your existing X compositor or write a new compositor based on that. Aside from that, the core Wayland library hasn't seen much work. We did run into some issues with thread safety, multi-thread use of the library, and it's some of the same things that Keith covered in his DRI3 talk, where we need a separate event queue to make sure we can block ETL swap buffers without interfering with the event coming in a different thread. So the initial assumption was that, well, there's always going to be a main thread because that's how toolkits work. You pull on the X file descriptor and you dispatch the events, and that should work right. But of course, if you have like QML will have a rendering thread that does. QML is a scene graph type of library for Qt, and so they have a rendering thread that sits in a tight loop, basically renders and blocks and swap buffer, renders again, and then synchronizes with the main thread. So they get a deadlock because suddenly the main thread is waiting on the rendering thread to come out of swap buffer, and the rendering thread is waiting for swap buffer to finish so we can signal the main thread. And so that doesn't work. So one of the things we did there was to have multiple queues that could, when you get an event, we automatically send it out to the right queue, so you can wake up and you don't have to wait on the main thread to do the event processing. And another assumption was that you can have only one thread can read from the file descriptor, and that doesn't work when that thread is sleeping. So a lot of these assumptions are gone now, and it's very orthogonal, multi-thread safe, and we can all these different use cases and thread scenarios that are possible because of the ETL thread semantics are now possible with Wayland. So we have a pretty solid base there, and it took a few iterations to get that right, but I'm pretty sure we have the right mechanism in place there now. And finally, we've done a lot of documentation. We have more main pages. We have more in the documentation in the code. So if you're trying to use the Wayland client library or the Wayland server-side library, there's a lot more documentation in there that documents these, like the threading model and the API there. But that's more or less what we did for Wayland. For Western, we did a lot of work for Western, and that's, in general, most of the work we do happens in Western. And while Western is a reference compositor for Wayland, it's the reference implementation, it's also something that's becoming a product in itself. So, and it's a little confusing when you look at Western, because it comes up as this as a toy desktop, and when you look at it, it looks like a very half-finished desktop environment. But what it really is a toy desktop sitting on top of a very efficient and solid compositor. So if you can think of it like the way if you run X with a toy environment on top of that, it doesn't mean that X is a toy. So the X server itself is useful for a lot of different use cases, but it has to come up somehow and display something, and that's what that toy desktop is. So a lot of the work we've done on Western has gone towards fixing bugs, making it more stable, and making it faster. And we have now use cases where we're going to use this in automotive. It's being used in products. So the confusion there is that it's often mentioned as a reference compositor, but there are reference parts to it, there are toy parts to it, but there are definitely also the core logic in the compositor is very much product quality. So let's see. So I have a big list here. I don't know if I want to put it up here, but this is basically what we've done for Western. So one of the things that landed recently is that we have libVA, which is an Intel library for accessing the hardware encoding functionality of Intel chips. And oh, we're going bigger. Well, yeah, I don't know.
There's a zoom under insert.
Well, yeah, I'm just still thinking that maybe I just want to not show it actually. Yeah, okay. Let's where's the zoom?
Under insert in the menu top left, there's zoom under that.
Yeah.
Yeah.
Yeah, let's do. There we go. So libVA is basically, you all know libVA, I guess. It's a library for encoding and decoding using the Intel hardware. And we hooked it up inside Western so that we now have a zero copy path from rendering a frame in the compositor and then feeding that frame into the encoding functionality, and then without copying anything, without taking data through the CPU, sorry, we can encode that most recent frame and save it to an H.264 stream. And it turns out that one of the features of newer Intel chips is that we have dedicated encoding ASIC chip logic on there, so we can actually encode on the fly very, very efficiently, and you can do screen capture without much, without much overhead. You lose a couple of frames per second in Sonotics when you run it, but other than that, you can basically capture the Sonotic at full resolution, at full speed. So it's very very cool feature. Another thing that we did was prime support or hybrid GPU, where you have this discrete GPU and you have the integrated GPU, and because of the way that this is implemented with the prime support and FD passing, it more or less just works because the Wayland protocol for sharing buffers is based on FD passing. So you pass an FD that describes the buffer, and on the compositor side, we'll take that FD and turn it into a texture and then render from that texture. And we don't really care if that file descriptor refers to a buffer that is on the integrated or the dedicated GPU. So it's almost exclusively a client-side thing, where on the client you can say, I want to run this client on the discrete GPU, and then you need a libEGL to look up that GPU and render, and then when you pass that FD rendered on one GPU to the compositor, we'll open it up and check it from it on the integrated GPU, and it just works. And of course, much of the heavy lifting here is in the kernel for the FD passing, but So it's great to see how easy that works. It's not completely finished yet because authentication, as Keith also mentioned, gets in the way. We have to authenticate, and to authenticate, we need to know which nodes are part of the compositor. So I think what we want to do is just wait for render nodes to land, and then the compositor doesn't have to know about external GPUs, so we can have compositor running on the integrated GPU, and the client can choose whatever GPU it wants to render on and pass file descriptors to the compositor. But again, a lot of this stuff is still pending, and once the render nodes land, we'll have a better story there. And we switched to DMA buff FD passing about early this year, where and this solves a lot of problems with lifetime, because the gem names of course it's a global name that anybody can open, but it's also something that's the lifetime is tied to the process that you have to pass it, and somebody has to open that name before the buffer is before you can safely use the buffer. But with FD handles, the FD handle will keep the reference to the buffer as it's in flight through the socket. So even if you pass the FD and that process dies, we can still on the compositor side open up that FD and access the gem buffer. So this simplifies the lifetime issues about buffer passing a lot, and also it makes it, as David mentioned in his talk, that it's a rights transferal. So it solves all the access problem we had before, where everybody can open a gem name. So that was pretty easy to hook up, and it solves a lot of problems. So that's a good feature too. So this ties into what David was talking about, that we have a lot of there's a few things that we need to do as root in a compositor or in a display server. Like we need to open input devices, we need to drop and set master, and there's some TTOI setup that may or may not require root. But so what we do in Western is we put all these privileged operations into an external helper that is a tiny application. It's 1,000 lines of code with no significant dependencies. So it's easy to audit this setUID helper, and then the core compositor, which links to libgl and lots of other libraries, will run as a user without any privileges. So it's a good split, and that's something we did early on. But what David has been doing now is that a lot of the work we've done in Western launch is going to be handled by lognd, so that instead of having Western launch run and do these things for us, we can open a dbus connection to lognd and ask lognd to open up input devices and drop and set master for us. And if we crashes, then lognd is there to clean up for us. So it's going to be we're going to take this chunk of privileged setUID code out of Western and put into lognd, and we're going to have a more robust setup, teardown and crash recovery. So with that, once we have that in lognd, there's going to be nothing privileged at all in Western. And of course, Western here is just one compositor. The same things here will benefit GNOME Shell or other display servers, or it can work for X as well. So X right now is setUID root because X needs the same things, but we could modify X to talk to lognd for input devices and drop set master, and then X can run without privileges at all. We have a backend abstraction inside Western that allows us to run Western on top of X as an X client, where it renders to an X window and gets input from X. We can run on a KMS and EVDEV. We gained a few backends since Nuremberg, where we got a Raspberry Pi backend from Daniel and his team. Mostly Pega. Yeah. And we got an RDP backend, which will start up Western as a as a headless compositor. If you have an RDP client, you can then connect to that server, and you get an RDP window up with kind of looks into that RDP server, the RDP desktop there.
And there's a Wayland backend as well.
That's a Wayland backend. Yeah, I think we had that in. So these are the new backends, and there's also I think down here there's an FBdev backend, so we can run on FBdev and EVdev. And FBdev is in itself is not terribly interesting, but Adrian recently added a libhybris backend, so when we can run on FBdev, we can use an Android driver to accelerate the GLES2 compositing. And Adrian's talking about adding support for the hardware composer as well, so we can hook into overlays or accelerated compositing hardware on the chip we're running on with the Android drivers. A cool feature that Alex Larson from Red Hat did is output scaling, which addresses high DPI displays. So displays like the new MacBook Airs with Retina displays or the Google Pixel have like ridiculously high DPI. And if you just run a regular desktop on these laptops, these screens, the pixels are just tiny and the fonts are unreadable. So one thing to do here would be to kind of tweak the DPI and just render everything bigger, but it's not the best solution. And what Alex has done is you can specify that an output is scaled, and then you kind of communicate that the size of this output is actually half the resolution of what it really is. So if you have a 2560 times, I don't know, but you basically report half the size. So if it's 10 by 7, you say this display is 512 times 384. So it looks like a smaller display, and applications that don't understand output scaling will render a window at that resolution, and the composer will scale it up to match the actual pixel size. But applications that do understand the pixel doubling will provide a buffer render at twice the resolution with twice the detail and twice the pixels, and the compositor will not scale those pictures. So we can have legacy applications scaled up automatically, and applications that are written to understand this will not be scaled up and look really crisp, but they'll all be the same size. They'll all be readable. So that's a pretty exciting feature, because it makes high DPI displays usable. And this is something that requires support throughout the stack. So Alex also worked on Gtk support for this, so that Gtk will pick up the scale property from the outputs, and if that scale property is set, Gtk will render at twice the resolution and communicate this back to the compositor. So it's a vertical feature, you could say. And Alex did it in Western, but GNOME Shell will have support for this as well, of course. So Gtk apps running on a GNOME Shell will get the same feature there. Richard Hughes also from Red Hat did support for color management, where this first step here is just support for loading color profiles from disk and applying these color profiles per output, so that you can specify in the config file for Western that you want to load a specific profile for a specific output. But there's also a different plugin that lets Western talk to ColorD, which is Richard's project to dynamically manage and configure color profiles, so you can change the color profiles at runtime with this plugin. We spend a bit of time on startup organizations for Western mainly, again, because we have some IBI use cases we're working on, and startup performance here is really, really critical. So a lot of the stuff we did was, first of all, compile we have a bunch of shaders we use for different color formats and different type of buffers, and we compile all of those up front. But an obvious case was to move this around and do this on demand. But some of the things we're looking at in the future is to go further and then start up with a software renderer based on Pixman, so that we can start up really instantly without loading or linking libgl, egl at all, and without even trying to initialize those and compile the shaders, but just bring up Pixman and render a logo or a splash screen, and then once that's on screen, we can start loading the rest of the GL pipeline. So that's something that's still ongoing. But it sounds silly because when you start up Western today, it starts up instantly on a modern laptop. But we're looking at doing this on system on chips, on Bay Trail, on embedded systems where we don't have the same CPU power, where shader compilation takes longer. So it makes more sense once you look at smaller systems. Let's see. Subsurfaces is a feature that Pekka from Collaborator did, and allows us to have put a surface on top of a different surface. To typically, if you have a different color space, you want to just display a YUV buffer on top of a window. Then that window may be RGB color space, and then you want to put a YUV buffer on top of that. And what you want to do there is you want to make sure that those windows move together as if it was just one window. And under X, you get this for free because X has the child window support, which is it's not used much today. Most toolkits just have one big top level window that they render into and do all kinds of event propagation and delivery client side. But there's still a use case where you do have if you have content in a different pixel format, you want to have a sub window and put that into your application window, and then you can render YUV content into that. Yeah, I mentioned this briefly. We can use Pixman for rendering now. So if we don't have hardware OpenGL, or we don't fall back to software GL, we can fall back to Pixman, which is still a much faster way to render, to composite, than using a full GL stack. So we have a more granular fallback mechanism that lets us use a different render path entirely to get fast acceleration, get fast compositing in case we don't have hardware GL. This is kind of a side project of what we've done. We have these two EGL extensions here that kind of fell out of the work we did. Initially, when we started doing this, we didn't use EGL surfaces, but we had like explicit management of buffers. So we would have like 3 buffers, and then we would say, okay, we set this as a current buffer and render to that, and then swap buffer, and then we would take that buffer out and reset a different buffer. So we had explicit control of what buffers were in use and when we used them and when we rendered to which one, and we could track what was rendered to that one, what was rendered to this buffer. So what we did was we basically had, we were able to track the difference between the buffer we were showing and the buffer we were about to render to. So we would know that to render the next frame, we have to first render this area to bring this new back buffer up to date with what's currently on screen, and then we render the new content on top of that. So instead of having to render the entire frame, we could just render the delta between current and the old buffer, and then a new frame. And in case where you have like a video playing or a spinning icon in a browser, then those two areas overlap. So what you often end up with is you take the old buffer, and you end up realizing that all I need to do is render the new content in that buffer, and you end up with your next frame that you can then page flip to. And that's what we did early on. And of course, we wanted to get to a point where we could use the EGL surface mechanism directly instead of this explicit buffer management. And Robert Bragg came up with the idea that we could we had different ideas on how to do this. We could have like explicit damage tracking in the API, or we didn't come up with a good way to do it. But then Robert said, maybe we can just have the buffer age that lets you query how long ago was it that I rendered to this buffer. And that way you can track the damage on the side in your application. You can use peak span regions or whatever mechanism you want to use for tracking. And when you're ready to render, you can say, how old is this buffer? And if it's one of the buffers you've recently seen, you know how much you need to re-render to get it up to date with the current front buffer, and then render the new content on top of that. And then that lets you minimize how much you render per frame. And I think this is really the most optimal way to do incremental repainting. There's been a lot of extensions in EGL for how to do this, where you can say, let me copy like these rectangles from the back buffer to the front buffer, or let me swap, and then you get a completed damage buffer. Or also in GLX we had Mesa copy sub buffer. So there's been different attempts at this, but I think this really is the most efficient way to do it, because there's no extra copies, there's no copy from back to front, there's no so you can always page flip, and you always only render the new content, basically. So it's a very efficient way to do this. And hand in hand with the buffer age extension is swap buffer with damage, where you say, once you do the swap buffer and you know that you've only repainted this new content, you can communicate to either the Windows system or the KMS. You can tell that as I'm swapping this buffer, you're getting a completely new buffer, but this region here is really the only area that changed compared to what you're currently showing. So for something like a display link device that's connected on USB, we can automatically determine what to actually push to that USB device from the damage we submit there. And of course, in case you're running on a compositor like Wayland, we send that damage information to the compositor, which will use that information to only repaint the part of the surface that actually changed. So they're two generic extensions. They're not Wayland specific at all. And once we have DRI 3 in X, and we can do complete buffer flips or buffer swaps for Windows there, we can use the same extensions there to communicate to applications that they only need to repaint part of the windows, and the compositors on the X can have the same optimization. Let me see the input methods. We've worked on input methods for Wayland. We have input support in the protocol, so you can have on-screen keyboards that you bring up, and they communicate with the clients. And the clients, this happens through the compositor, so the compositor will invoke the keyboard, bring it up, and place it on the screen. And clients will get input at a text level, not as a key press level, but text events. And it works fairly well, but it's still pending review. So once we get GNOME Shell up and start the deeper integration there, we'll have to see how that interface works in real life. But it looks promising so far. It looks like a good interface, and we will see how it holds up once we start using it in GNOME Shell and other desktop environments. Wayland is moving along as well. It hasn't fundamentally changed what it does. It's still a mechanism to pull in X windows from X into Wayland, and it can do top-level windows, or it can do a full-screen X server. So that's always been there, the two modes of operation. What we do in Western is that we pull in top-level windows, and we get those windows into the compositor as Western or Wayland surfaces. And what we've done there is mostly correctness, bug fixing, and maturity. There's nothing fundamentally changed in the concept there. One of the things we did do was copy and paste between X Wayland clients and Wayland clients, as well as drag and drop between X client and Wayland clients. At least drag and drop works in one direction. But we'll figure out the other direction as well. And one of the things was that we did this work to figure out if there's anything we need in the X server to do support drag and drop or copy and paste. And it turns out that all this stuff can be done in the window manager, as long as we have the window manager inside the compositor. So in the external projects, there's a lot of activity around Wayland as well. Of course, the big news is that GNOME Shell is now more or less ported to Wayland, and GNOME 3.10 was released today, and there is preliminary Wayland support in there. I think the best way to try this out would be to try out a Fedora 20 preview, which is coming out with Wayland support in GNOME Shell as a tech preview. So I think it's going to work in GDM, you can select Wayland as your session type and log in as normal, and that will bring up a GNOME Shell as a Wayland server. So it's something that's not enabled by default, it's not even installed by default, but it's going to be easy to install the RPMs and then select it from GDM, and then you log in and you're running Wayland. And ideally it shouldn't look terribly different from how it normally looks. It's still using the same technologies, and it's still it's still being an X window manager, but the difference is that instead of going through X for page flipping and rendering, it's talking directly to KMS now, so page flip will turn into a KMS page flip. Input events comes directly from EBDEV devices into the compositor, which uses a scene graph to determine which applications you get it and how to transform the input event according to the transformation of the surface. So we can do these things correctly now. We can shorten the path from input event to application, and there's a lot of small optimizations that can be done later on. But the initial preview here is a tech preview, so a number of things won't work. A number of things will be flaky, and it's also not at the point where it takes advantage of all the things you can do. One of the things that I like to see sooner rather than later is that we can make GNOME Shell actually have a different surface for each output. This is something that Western has always done, but GNOME Shell comes from being an X compositor, and the internal structure is still set up. We use it through Clodder and Coggle, the rendering libraries that it uses, to have one big surface for all outputs. But one of the low-hanging fruits there is to split that up and have a different surface per output, so that we can have a buffer, separate allocated EGL surface per output. We can page split them independently, and specifically, if nothing's changing on my screen here, but I'm running something on the projector, we don't have to update this screen here. And also, if you plug in a new screen, you don't have to mode set your current display to bring up a new external monitor. So there's a lot of details where we can add polish and make things work better once we start taking advantage of GNOME Shell sitting straight directly on top of KMS. So GNOME Shell is definitely furthest along, but Enlightenment is also working on Wayland support. I think I'm not sure if this is something they announced yet. I'm not sure, but there's Enlightenment 19, which is coming out sooner than I think they had a long cycle for Enlightenment 17, and 18 is almost out again, and then 19 is going to be another half-year cycle. So that's for Enlightenment 19, they expect they'll have Wayland support, and that's like a half a year out, I think. KDE is working on Wayland support, and I'm not so sure what their status is, but no, Martin, the KWin maintainer, works on this pretty actively. So he's working towards KWin as a Wayland compositor. One of the things that were always challenging with Wayland, or at least difficult when you port from X to Wayland, has been browsers, like the Webkit browsers, where you have like some kind of cross-process buffer sharing model for safety. So different tabs in Chrome will run in different processes. They'll render their content and push that content to the browser. The main browser process will then take these content, these tabs and composites together. And under X, you can render to a PIX map and share that PIX map with the other process, and then the main browser process can take from the PIX map into the browser, or you could even just have a sub window that you ask the external process to render to. But we have answers to these approaches now, where Chromium, for its out-of-process model, actually has its own IPC mechanism where it serializes GLES2 rendering. So you fork out of a process to render a tab, and that process will send rendering commands back to a render process. So there's no need for buffer sharing in this model. So that's the easy one. The other one is the case where you have a compositor that actually you do rendering in the different tabs or different render processes, but you have a main process that then will take those surfaces and takes it from them to composite the final browser. And the answer here on the Wayland is that you run a nested Wayland compositor, so that the browser itself will act as a Wayland compositor to the tabs, and the tabs will then start up as Wayland clients off that browser and push their textures back with EGL swap buffer or whatever rendering mechanism they're using. And there's a bit of boilerplate in setting this up, but once that's out of the way, it's actually an efficient mechanism that reuses the hardware enablement. They reuses the EGL platform that you've enabled once for your chipset or for your driver. So it piggybacks on the existing hardware enablement for Wayland. And it's also a point-to-point communication mechanism between the browser tab and the browser, where on the X, when you render to a PIX map, you render to PIX map, you notify X, and X will then notify the browser back. So there's one less round trip in this process. So it sounds awkward, but it's actually a very efficient way to do this. And one thing we have on the this currently you need to do still need to composite that, and there are a few things we can do to make it more efficient, but those use cases are well understood now, and we have answers for those cases. Yeah, let's see. Let me just jump down here. What's the? Am I going over time here? Yeah, a bit. Yeah. Okay. So also another exciting development is a Jolla Phone, which is a lot of Nokia guys that left Nokia to form their own phone company when Nokia decided to go with Windows. So they formed Jolla and started doing a Jolla Phone. And they basically based off of the MeeGo OS that Nokia was using before they jumped to Windows, and they took that and kept working on it, and they moved it to Wayland, and they're now shipping a phone running with the Qt 5 on Wayland. And they're using their own compositor, but they're using the Wayland protocol between Qt 5 and QML and their compositor. And another interesting direction is Geneva, which is an industry group from an automotive industry group where they're working on defining standards for software components, open source software components that you can use in automotive infotainment systems, so like entertainment and information display. And they've chosen Wayland as their recommended display protocol, and they're using Western as a reference compositor for there. So it's interesting to see where this is going, and I think we could expect Wayland to show up in cars eventually. So that's pretty exciting. And let me see. Toolkit support. So Toolkit support is moving forward. GTK is pretty much complete now. There is still drag and drop needs to be supported, but that's about the last feature that's missing. everything else is there. Yeah. Did you want to show the Raspberry Pi stuff? Yeah. I don't have a lot of demos myself here. I would have loved to demo the GNOME shell, but I haven't been able to get it running recently. But hopefully, this should be really easy to run soon when they get the snapshot out, and you can just download it, install it, and pick Wayland in the GDM menu, and then it comes up. Yeah.
Yeah, so this is, once it eventually boots, going to show a backend we did for Raspberry Pi a little while ago, and have been working on since at Collabora. It's mostly not me. I've only ever really fixed Wayland for it, to be honest. The Pi's kind of a special case of ARM, which is pretty dire to begin with. But then it's basically a set-top box style and quality video compositor, which is enormously high bandwidth and great at compositing multiple streams. And then they kind of tacked this ARM v6 on the side of it, or ARM 9, which, I mean, even the Nokia N800 had a more powerful ARM. You're going back to 770 for that class of ARM, so it's horrifically slow to begin with. And then the memory access model is really weird. You incur massive latency, and there's basically no cache either. So it's kind of the worst case for X, because if you want to do any kind of effects, you have to go to an external compositing manager, and that means you're not actually using any of the compositing hardware, you're trying to shove it all through GLES instead. And yeah, in the server you get slammed by implicit rendering all the time. Like, your server just ends up blocking hideously on extremely slow software operations. So we wrote a new backend and renderer which doesn't touch GLES at all. It shoves the entire scene graph into the display hardware. And I mean, we've done a few other really dull things as well, like V4L drivers, which aren't that interesting to you guys. But yeah, so this is just a standard spinny triangle EGL client. We did a couple of other shiny bits as well, like the world's worst implementation of Expose, which I literally didn't write the night before we needed to demo it to the Raspberry Pi Foundation to prove we'd actually been doing things for them. But you know, that's not a limitation of anything other than my skills, where we don't have a sort of packing and layout framework to work with. We also did a bit of work on Webkit Gtk. That's Webkit 1, so you can imagine if we tried Webkit 2, it would start up even slower. So we're not going to do that. I'd like to apologize in advance for the choice of video. Oh no, I can't. Nice. Right, I was going to show Big Buck Bunny playing fully accelerated, and it actually handles 720p, 24 or close to 30 FPS coming through. But since we've combined the window manager and the compositor, we can use any amount of the hardware to feed in any ridiculous effects we can represent, whereas with X11 it's GLES or go home, really. Yeah, there's also, like Kristian said, we did some stuff with Wayland. I just pushed a random X server build into here. I don't know how well this is going to go, if I'm honest. LibreOffice also isn't particularly quick to start up here. Can probably take some questions, I guess. Anyone? Oh, that shouldn't be transparent. Oh, that's a opaque region. That's all right. We reported the bug to them because that's in their firmware. So literally not our fault.
Yeah, I was just quite interested in your software transitioning to hardware mode for fast startup. Not for this, but for Kristian's part of the talk.
Right.
We're looking at doing that as well, and one of the things we want to do it for, because we're insane, is to prompt in the init ramfs if you need to unlock your root file system. Is that something that that doesn't sound like your use case, but is that something that you think you're interested in?
You want to run from the init ramfs?
What's that?
Do you want to run from the init ramfs?
Yeah.
I don't think so. I think like for the cases we're looking at, which is mainly IVI driven, that we're looking at trying to get from power on into Western running within 2 seconds. And we can do that with the right bias and with the right systemd setup and without init ramfs and without anything. So we just boot straight into the system and we get up and running early enough that we can run Western. And if we do this right, we have like 400 milliseconds from Western starting to, with that 400 milliseconds left, those 2 seconds. And if we do the Peaksman renderer, we can within those 400 milliseconds we can get on the stuff on screen fast enough.
So
cool.
Various governments have laws about how long you can take until your backup camera comes on the screen. So is that compositor good enough and fast enough to use for those? I mean, so you can have the backup camera with the overlays over it?
Yeah. So what we're missing there is that we need to figure out the right overlay camera to use, which is kind of out of our scope. But once you have an overlay camera that captures into a YUV buffer, we have we can actually, well, ideally then we can take that buffer and put it in a sprite. Are you done? Yeah. Okay.
No, I have a video if you want. I'm putting it on a USB stick if you want to show it.
The bunny.
It promises it's not too gross.
It kind of only runs in WebKit at the moment.
But you can open it from the USB stick, URL with the files.
Also, I don't have any spare USB ports.
Don't worry about it.
It's fine.
Yeah, we've seen the bunny before, and
Yeah, no one wants to see Big Butt Bunny again. I don't.
but yeah, so we get that stream from the camera, ideally in YUV format, that we can directly show on a KMS sprite. So one of the things, can I switch over here?
Yeah.
I can do some. So is that? Oh, okay. I am. On VGA, okay. So computer one, I think. There we are. See if we can do this. Right. So this is Western running here, and
Quickly to answer Dave's question, if Raspberry Pi is going to pretty up Western. Yeah, so the expose thing I demonstrated, and there was also a kind of subtle fade effect where we darkened all the layers behind the active screen. There's a few bits like that and just kind of vague niceties that we're working through pushing upstream. But you know, it would be nice to keep on going because their stated goal is to have that as the Western desktop experience. But I really don't want to write another desktop environment Kristian doesn't. Like,
Right.
and so, yeah, we'll see how far it goes.
Yeah. This is a debug mode for Western. So the idea is that once you do this, everything that goes through the shader, through EGL, gets a green tint. And you can see how the cursor doesn't have a green tint. The cursor is a regular surface like any other surface. And it's only in the very last step in the back end that we decide that the cursor is actually something we could put in a hardware cursor surface. So that gets put in there. So right now sprites are disabled, but what I want to show that we do have Sprite support where KMS you can put a surface if it's opaque, and well, it depends on the sprites, of course. For the you're not using KMS, but you have overlays that are alpha transparent, and if we had alpha transparent capable sprites in KMS, we could say something like this terminal. We could put that in a sprite, and then that would scan out instead of being rendered. And when we do the debug mode, the terminal would not have that green tint as well. But going back to the startup and the backup camera, so ideally we'd take the data from a backup camera and just put in a sprite, and then we could start up and show this right away. As it is, if we want to do a backup camera, we have to do YUV to RGB color space conversion, which typically means we have to pull it through a shader to get that conversion done, and that means that we have to start up a little slower, or show a logo, load the GL driver, and then have the backup camera. So, but anyway, I think we don't need to do the init RAMFS tricks because we get up and running pretty fast with systemd and the BIOS that we're using. So.
Oh, right. I wasn't thinking about your specific IVI use, which
Right.
clearly wouldn't. Well, I was thinking about desktops still exist and.
Yeah. I think the plan is to still have something like Plymouth, a special case, Splash for. I mean, again, this is more a Red Hat question. What do the Fedora guys want to do here? Do they want to keep Plymouth? Do they want to do something else? But it's something that I don't think you want to start up Western in the initRD, because you end up with you run the process from that file system. You can't unmount the init RAMFS. You really want a new gold process that can come from that file system so that you can do the change route and unmount properly. So that's really the biggest problem. The other problem is that you have to put EGL drivers in the init RAMFS, and then we can go back and talk about Mega drivers again.
Not if it's a software renderer.
Right. Well, yeah. So yeah, that's a good point. So you could start up in the initRD with a Pixman renderer and just pull in Pixman and use the KMS DOM buffers, and then you could do that. But so it's really only a question of doing the switch route and unmount. Adam.
Doesn't seem like there's a lot. I mean, we already have a Pixman-based renderer in the init RAMFS.
Yeah.
Making it a Western composite really.
And
We could split up the unlock dialog and something else.
Yeah.
Maybe that's exactly. But what are you like? What problem are you solving?
Right. I mean, I don't think there's that much use, much they'll cheerlead for Wayland all day. I don't think that there's that much use running a Windows system for something which doesn't have any Windows. Like, you just need to blit. And we have Western launch, like Kristian was mentioning earlier. It hands off all the DRM devices to you, so at some level it already knows about that. So it wouldn't be too much of a stretch to get some kind of handoff protocol there if you wanted smoother transitions.
And I mean, on the bottom of both of those individual flash disks, we can get out the process so quickly. That displaying you when it's flash all on the whatever. Maybe the bigger key. 2 seconds.
yeah.
Yeah, even gets out of init RAMFS really, really quickly. But then if you want to deal with GLES, you have the whole thing of create a context, 16 meg gets allocated. So we'd rather not.
So let's see. The rotate? Oh, yeah. Oh well. Yeah, rotating. I don't have any wobbly windows today. But it may happen. We may. But we'll see. Yeah, Sam's looking into that. So we have a fairly simple renderer backend that can't do like wobbly windows or tri meshes, but it just does like windows potentially rotated. But we may do that as long as it doesn't incur any kind of performance hit when it's not enabled. Yeah. Anyway.
I did fix that black flash when we map Windows under X Wayland.
Yeah, that's a composite sync, right?
No, it's an extra point.
Oh, okay, yeah.
One line removed.
Let's
Best
do it.
fix.
Let's do it. Okay. Yeah, so I don't have a lot of stuff to demo. It's just my big list of stuff basically. But any questions?
Probably one thing worth pointing out as well is the subsurface stuff. Compared to X, where you have this window tree where loads of stuff just happens async. So, you resize and you resize the frame window, then you resize the content window, then maybe sometime later you resize your sub window for video inside that. And it's all a bit of a don't look behind the curtain, massively desynchronized mess. So one thing we did for subsurfaces is, in general, they run async like that. But if you want to either resize, or the other classic case is scrolling a web page with embedded video, where you want the flip to newly scrolled content and the move of the video window to occur at the same time. We introduced a synchronized mode for that, where the parent at the head of the subsurface tree is in control, and so it can ensure that it and all its children are in a completely consistent state, so you get that atomic presentation. And we even have test cases for that.
All right. Well, I guess this wraps up the conference. Yeah.